Hi class, this is our first video of our new unit, Unit C, the unit on energy. And this video is about introduction to work and types of energy. So what we're learning about today is a bunch of terminology related to work and energy. And we're starting to understand the relationship between energy and work. Oh, I found some memes about work, and I thought I would show them to you. It's really important in this unit, as all other units, to show your work. Okay, so what is work? So work is, work occurs when a force or a component of a force displaces an object. So for example, this horse pulls on this cart with 35 newtons force over a displacement of 12 meters. So that horse, the force of that horse is doing something useful. So notice that it says occurs when a force displaces an object, but it also says when a component of a force displaces an object. So if there is a component of a force that's in the same direction as the displacement, work will be done on the object. So you can apply the force in the exact same direction as the object would move, or in somewhat of the same direction as the object would move. So the simplest way to calculate work is in a situation where force is parallel to the displacement. So force and displacement are normally vector quantities, but here we're going to sub in the magnitude of the force and the magnitude of the displacement and just simply multiply them together. So F stands for magnitude of the force, delta D, magnitude of the displacement, and these are SI units of newtons and meters. So when we multiply them together, Newton meters, that combination of units happens often enough in science that it is designated joules. And notice that because they're magnitudes of vectors, we have a scalar the scalar answer when we multiply those two scalars together. And so 1 joule is equal to 1 Newton meter. So a 1 Newton force would move, a 1 Newton force causing an object to move by 1 meter would require 1 joule. You'd have to do 1 joule of work on that object. So sometimes in a problem you are given your force and your displacement, and if they are parallel to each other, then you can sub right into this formula. Sometimes though, you'll have to calculate the magnitude of the displacement through kinematic equations. So let's do kind of a visual example. If we calculated the work done by this horse, we would simply do this force times this displacement, because the force is in exactly the same direction as the displacement. Let's try this example. So calculate the work done by the horse, work done by the horse, if it applies a force of 35 newtons to accelerate the cart from rest to a velocity of 8 meters per second forwards in 3.5 seconds. So one thing to note about the wording of questions in this chapter, work can be done by the different forces acting on the object. So on this object, we have the force of gravity, we have force of friction, we have the applied force of the horse pulling this cart. But on this cart, there would be more than one force on the free body diagram. But since we're looking for the work done by the horse, we just need to know the force applied by the horse on the cart. Do we have enough information? Well, work is the product of the magnitude of force and the magnitude of displacement. We don't actually have the displacement. So let's organize our givens. Let's organize our givens. We have initial velocity because it says it's from at rest, final velocity of 8 meters per second, time of 3.5 seconds. So these are actually quantities that come from the kinematics chapter, from unit 1. So we can find a kinematic equation that connects VI, VF, and T with the thing we're solving for in our first step, which is D. So we substitute in our numbers. VI cancels to 0, and it's simply 1/2 VF times delta T to give us our displacement, which is 14 meters. Do not be tempted to just multiply the velocity by time. You might see the units and say meters per second for 3.5 seconds. You just multiply them together. That would be if your velocity does not change over time. But since we are accelerating, you can never do velocity times time to get displacement. So V equals D over T does not apply when velocity is increasing over time. So when velocity is increasing over time in a steady way, that if you remember, this is what uniform acceleration looks like. The displacement from the VT graph is the area under the curve, which is 1/2 base times height. And that is just all another way of looking at how to find displacement. It gives you the exact same math as going with the kinematic equations. So as it just going with the kinematic equations and you find your displacement. Now, if we need to find work, and work is force times displacement, since they are parallel, this is the simple equation that we use. 35 newtons times our calculated 14 meters. Now, if this was a decimal value, we're not going to round it before we carry it forward. And then we get 490 Newton meters or joules. So work is equal to 490 joules. And the way that we report it in this chapter, it's important to write therefore statements, because you can't just say work. You'd say work done by something on something else. So you'd say 490 joules of work done by the horse on the cart. So you'd have to say by the horse on the cart in order to get full marks for that therefore statement. Okay, so in our previous example, the force was pulling in the exact direction, in the exact same direction as the displacement. But what happens if we pull up at an angle, or if we pull down at an angle, and only part of the applied force is in the direction of the displacement? Well, then we have a more detailed equation for work. It is more accurate. It is F cos theta D. And now what this piece here is the force, the component of the force that is in the same direction as delta D. So if this is delta D, it's the component of the force that is exactly in that direction. Notice that there are some ways in which this equation will simplify to case 1, where F and D were parallel. If theta was 0 degrees, then this equation simplifies to force times displacement. Theta equals 0 occurs when force and displacement are parallel. So case 1 and case 2 are not totally different. Case 2 just applies for a wider variety of cases. And if force is up at an angle, you can't use the case 1 equation. You have to use F cos theta D. Just a little reminder about how we do components. So where does that cos theta come from? If we want the horizontal component of a vector at an angle, you would write a right angle triangle, and the horizontal component is adjacent to theta. So cos theta equals this x value divided by the hypotenuse. We rearrange that for this x value to get F cos theta. So that's just a reminder of how we get components. In this case, the way to get the component is already built into the equation. Okay, let's try another example. So in the second example, we've got a mover that maybe they're taller than the box on the sled, and they're pushing down at an angle that's 25 degrees down from the horizontal, and we're given their force, their strength is 55 newtons. So we're given 55 newtons at an angle of 25 degrees down. We're given displacement of 8.5 meters horizontally. They are not exactly parallel, so we have to use the more full equation. You can always use the more full equation when in doubt. Cos theta might simplify something to give you a simpler version, but it's always a safe bet to start with the full one. The angle theta is the angle between F and D. So the angle between force, which is this red here, and D, so if we put the red, if we translate that red arrow onto the black line, there are 0 degrees between them. The force is at an angle downwards. If we translate this black angle to the black dotted line, there's an angle of 25 degrees between them. So 55 cos 25 times 8.5 is equal to 420 joules. This goes without saying, but make sure you know how with your calculator to type in the angle. Sometimes you have to do 25 and then type the cosine button, and sometimes it's cosine and then the angle. So make sure you don't accidentally type into your calculator cosine of 25 times 8.5 degrees. So just make sure that's that bracket that there, or you know how to work your calculator. So 420 joules of work is done on the box by the mover. So some sort of therefore statement that specifies some details about that 420 joules of work is necessary. So just a note here, 420 joules is what's capable if this mover is only as strong as being capable of 55 newtons. If the worker was smarter, or maybe if they were shorter, the force would be more useful because theta would be equal to 0. 55 newtons times 8.5 meters is 460 joules of work. So more work could be done on the box if the person was pushing exactly horizontally with that same force, or if they were shorter, they wouldn't have to think about it. So sometimes it's a benefit to be shorter. So there are more special cases. So the first case was the special case where F and D were parallel, and then work was a calculation of force times displacement. And then the second case wasn't so special. It was the general case, F cos theta D gives you work. Now we're going to look at special cases where work can be equal to 0. So 0 work occurs if there is no force, or there is no displacement, or cos theta is 0. So if there is no force, remember that's cases where objects in motion remain in motion. Maybe there's a figure skater that is gliding across frictionless ice. They are not applying a force forward. There's no friction backwards. It is just, there is no force. They could be at rest, or they could be traveling at a constant speed, or there is no force, then work would be 0. If there's no displacement, so if I push, let's say if I push on an elephant as hard as I can and the elephant does not move, since there is no displacement, there is no work done on the object. And then the third way is if cos theta is equal to 0. If you have done this in grade 11 math yet, then you would know in the cosine theta graph, cosine theta x-intercept happens when theta is 90 degrees. So when the force is perpendicular to the displacement, let's say the force is going up and displacement is going to the right, there is no component of the force that is helping or hurting that displacement. And so work would be equal to 0. We can also have negative work. So that's another kind of special case. When the force is applied in the direction opposite to the displacement. So when the force, or a component of the force, is opposite to the displacement. So cosine theta, once we're bigger than 90 degrees, up to 180 degrees or between 90 and 270 degrees, cosine theta function will be negative. So if we take a look at this weightlifter, it says determine the work done by the weightlifter is positive or negative. Well, theta, if we're talking about the work done by the man, then we sub in the force of the man. I guess man or woman, weightlifter. The applied force is equal to Fg. There is a big assumption here that the person lifts it up at a constant speed, which may not be, that may not be realistic. You'd have to have a lot of control to lift it up at a constant speed, but that's an assumption we're going to have to make here in order to say F applied is Fg. So mass times gravity gives us our applied force. We sub that in here. And then cosine of 0 times 2.3. So that product gives us 2100 joules. Notice this is positive. We are doing positive, the woman, the weightlifter does positive work on this barbell. As opposed to gravity, when we are lifting the object upwards, so the displacement vector is up, Fg is down, the angle between is actually 180 degrees. Cosine of 180 degrees is -1. The work done by gravity is negative 2100 joules. So you can see why this is our first example where we're talking about work done by different forces. You can see why it's important in the therefore statement to be specific about the work you're reporting. So the work done by the weightlifter is positive 2100 joules. The work done by the weightlifter on the barbell is positive 2100 joules. The work done by gravity on the barbell is negative 2100 joules. In previous units, we sometimes got a negative and it was a vector quantity, and I said never report that negative. In the scalar world, it is okay because we're going to learn that that is a decrease in energy. Okay, so there is another kind of special case, finding total work. Finding total work on an object could be the sum of the individual work values. So for example, we have this person, this shopper, applying a force on the cart to the right, and the displacement is to the right, and the force of friction would be the opposite of the direction of motion. We could find the work done by the person and the work done by friction and add them up, realizing that this is going to be a negative work and this is going to be a positive work, so it's really a subtraction. Or the other thing that we could do, it's kind of a shortcut and I do recommend doing it, is calculating total work by using our regular work formula, but subbing in net force. So you'll have to do a free body diagram before. So in fact, let's solve that problem with the shopper. So we've got a shopping cart pushed with 41 newtons by the shopper, and the displacement is 11 meters to the right in the same direction as that force. The cart experiences a force of friction of 35 newtons to the left. Calculate the total mechanical work done on the shopping cart. So the first step here, since we want net force there, we want to calculate a total work. So this whole piece here is total, so net force. We do a free body diagram first, which is F, so that we can write our F net statement, F applied minus FF, that gives us our horizontal F net. Our horizontal F net is 6 newtons, and we sub in the 6 newtons into this formula to get 66 joules. So a total work done on the object is 66 joules. There are a few links to some really good work and energy resources that I'm linking to the end of this video. So just to check your understanding, so sometimes force is parallel to displacement. So in all of these objects here, we're assuming that displacement is to the right. we can calculate work by force times displacement, or if the force is at an angle, we can do work equals force cos theta times displacement. Or if displacement is to the right and force is up, that would be a 90-degree angle. That would be zero work, because we could still write work equals F cos theta D, but cos theta, the cosine of 90, is zero, and overall the work would be zero. And what if work isn't constant? So all of those cases above, those formulas for work, we're all assuming that that force that you sub in is constant. So really this should say, what if force isn't constant? So let's say over displacement. So we start moving an object from 0 to 10 centimeters away from the starting point. And at first, we're pushing that object with 5 newtons for 5 meters. And then maybe we get tired and we start pushing it with less and less force, but we still are moving forward as long as we have a net force forward. So force decreases in this zone. It turns out that work is the area under the force displacement graph. So there is one practice question where you have to calculate work given a graph, and you'll do that by adding up the area of one section, the area of a rectangle, and the area of a triangle, as we did in the motion graphs. So let's talk about types of energy and what is energy anyways. So if work is defined as the change in energy, and energy is defined as the ability to do work. This is a little bit convoluted. The definition for work is in energy, and if you don't know what work is, you look up work and it has the word energy, so it's kind of cyclical. So maybe those definitions are not that helpful. So there's an analogy that seems to work. So think to yourself, what is money? So money is our currency. We save up money, or we can spend money. Well, similar to money, energy can be thought of as the currency of the universe. So we can save up energy and to spend it later. So we'll learn that energy saved up or stored is called potential energy, and energy that we might spend could be kinetic energy. So now work is the change in energy. So we can save up energy. So if energy increases, the delta E will be positive, or the delta E could be negative. Since we know that work is measured in joules, we know energy is also measured in joules based on this equation. And we know energy and work are both scalar. And since energy is we already know that work could be positive or negative. And what's the meaning of that? That work that was negative work means that the energy of the object is going down. And positive work means the energy of the object is going up. Okay, now if we're going to be working with energy, all unit, for this whole unit of study, we'll need to know and be able to be comfortable converting energy units. So let's talk about 1 joule. 1 joule, which we talked about as a Newton meter, is not much energy. A 60-watt light bulb only emits 60 joules in 1 second. So that's what 60 watts means. It's the number of joules in a second of light emitted. So 1/60th of a second out of a light bulb is 1 joule. So that's not very much energy. And so my point here is that we'll use prefixes like kilo, mega, and giga to talk about our bundles of energy. So you'll notice kilojoules, megajoules, gigajoules, that's no surprise that those are still energy units, but kilowatt hours, that looks like power instead of energy, but when we come to the power equation, you'll realize that power times time is energy. So this is the way that we pay for energy in terms of kilowatt hours. So it makes it a bit easier to understand how an appliance rating would work if there was an appliance, like a light bulb. There is it's 60-watt light bulb. So if we run that for 1 hour, that's 60 watt hours of energy. So that would be 0.06 kilowatt hours. Anyways, these conversions can be used in our unit analysis to convert from one unit of energy to another. So if we take a look at some energy unit conversion practice, so if the average family consumes 16,000 kilowatt hours of electrical energy in 1 year, what is the equivalent in watt hours? So although kilowatt hours is it's a unit of energy, we can use the conversion of 1,000 watts for 1 kilowatt. We want to cancel out kilowatts, so we put 1 kilowatt on the bottom. We want to go 2 watts, so we put 1,000 on the top, and you end up with 16 million watt hours. What if we want to convert to joules? Well, you're going to write, again, the number you're starting with on the, start with the number you're converting from, and that's kilowatt hours. Then we put kilowatt hours on the bottom, and you're going to take a look at our slide to see if there is a conversion from joules to kilowatt hours, and there is. 3.6 times 10 to the 6 joules is 1 kilowatt hours. So we can cancel out the kilowatt hours, and on our calculator it's this times this to give us 5.7 times 10 to the 10 joules. So there's different types of energy, and all energy falls into 2 categories. Energy that's stored, so-called potential, or energy of motion, so energy that we can kind of see, kinetic energy. So we're going to talk about a bunch of different specific types of energy, and they are all either potential or kinetic or a combination of both. So we've got kinetic energy, which is energy possessed by randomly moving atoms or molecules. That's a combination. So we're going to have an entire chapter on thermal energy. There's sound energy, energy possessed by large groups of oscillating atoms and molecules. So those waves are sent. It's kind of like the motion of the waves, as if the wave has the wave is traveling from the speaker to the ear. We have an entire unit on sound energy. Gravitational potential energy, that's a form of stored energy. Objects, due to their height, have a stored energy. And there's evidence of that when you let go, that energy is turned into kinetic energy. So we can see that it's a stored form of energy. If we lift up an object, we can let go, and that energy, spending that energy on its way down, will do something useful, bring the object closer to the earth. Elastic energy is another form of potential. That's energy possessed by materials that are stretched, compressed, or twisted and tend to return to their original shape. It's a form of potential. So when we wind up that object in that elastic band and we're holding it there, we are storing that energy that we can, so it's like we're saving up money, we're saving up energy that we could use later. If we release it, then it can do something useful. Like it can turn into speed or height. Chemical energy, this is another form of potential energy. So it's energy stored within the bonds. So for the glucose molecule, there's energy stored in the bonds that if we were to break those bonds, we can release that energy. Electrical energy is energy possessed by accumulated static charges. So all of the potential energy is, I always think of it as compared to back to gravitational potential, because I can see it and it can makes the most sense to me personally. So if I think of lifting up the ball, I'm storing energy, I'm saving up energy that I could use later. So if I let go, I can use that energy to do the useful thing of bringing the object closer to the ground. I store up the energy by winding up the object. I've stored the energy in the bonds that I can use later. If you think of about a battery and you've got a negative terminal and a positive terminal, it's as if you're holding all the negative electrons at the negative terminal. And once you connect the wire to the light bulb and then to the other side, you're providing a path from the negative side to the positive side to allow the electrons to travel from the negative side to the positive side. So when you charge up a battery, it's like you're lifting up the electrons to the negative side of the negative terminal. And then when you connect the wires, providing that path, it's like you're letting go of the object that you were lifting up. So charging up a battery, you're building up potential energy. Radiant energy, we have energy possessed by oscillating electric and magnetic fields. We learn about this a lot more in grade 12. Nuclear energy is also known as atomic energy. It's energy possessed by protons and neutrons in the nucleus. And we're going to learn about that in a chapter of this unit. And today is the day you finally learn about this famous equation that you've probably heard about, E equals mc squared, which is associated with Einstein and modern physics. And what is this equation? It is the rest mass energy equation. Rest mass energy is total energy that an object has due to its mass. So we're actually going to learn how to use it another day, but now you've been introduced to it. So if your parents ask you, what did you learn today in your video lesson? You can say, I learned about Einstein's E equals mc squared. Interestingly, c is the speed of light. And it just happens to be that that is the constant that relates mass and energy. So it's really, really cool stuff. This is modern, considered modern physics. Okay, so those are our topics for today. I'm just hinting at what we're going to do in a future lesson. So this is a preview. We've learned about all these different types of energy. Energy can be transferred to a different object, or the energy can change form. So if it's changing form, it's called a transformation. If it's transferred from one object to another, it's called a transfer. And we're going to learn soon that transformations and transfers can occur in a closed system without creating or destroying the energy. So as an example, when we lift up an object, it possesses gravitational potential energy. When we let go of that object, the energy, the gravitational potential energy is turning into increasing kinetic energy. Then when that object bounces against the floor, we've got thermal energy. There's the heat from friction. We also probably have some sound energy, and then the object goes back up and gains gravitational potential energy again. The total energy, amount of energy at any point is equal. So when it's halfway down, it has some Eg and some Ek. When it's all the way at the bottom, it has maximum Ek. When it bounces, it loses some to the environment. There's another example here, photosynthesis. So the energy, radiant energy from the sun goes into the process of photosynthesis, which allows the plant to take water and carbon dioxide and turn it into glucose and oxygen. So we've got radiant energy from the sun that turns into chemical potential energy in the glucose food, because that's what photosynthesis is the plant making its own food from the sun, basically. Okay, now it's time for you to do some practice questions. Please make sure to submit your Google Classroom tasks, including the exit ticket for this video, including a picture of these practice questions. Don't forget you have the Forces Unit quiz to complete as well. Have a great day.